Good afternoon. I'm here to present my undergraduate research project. Not working. Oh, here it is. So one of the primary objectives of the LRO extended mission is to create an inventory of Copernican and Eratosthenian craters. And the reason behind this is that it helps us to investigate crater degradation rates, relative age OMAT size composition correlations, and also enable comparison with Mercurian craters. Previous work includes Williams Global Crater Catalog, which consisted of 250 Copernican and Eratosthenian craters larger than 30 kilometers in diameter, using Apollo and lunar orbiter images. Also, Greer's crater catalog, which consisted of 50 Copernican and Eratosthenian craters using Clementine's optical maturity parameter, or OMAT. And the most recent catalog was by Nuno et al., which consisted of 1% of Copernican craters and 12% of Eratosthenian craters from a global database of 927 craters. They found that radial reflectance was useful for classification, but not sufficient, and that most craters were located in the highlands. The methods that we used here, the main data sets that we used here was the LROC wide-angle cameras normalized reflectance map with an incidence of 60 degrees, the LROC WAC global monochrome mosaic, also with an incidence angle of 60 degrees, and crater shapefiles. We had two shapefiles, one for diameter ranges of 10 to 20 kilometers, and the other was 20 kilometers and greater. So the first method we used was the Williams classification scheme. So the images that you look, that's on the left, on your left, is the WAC global monochrome mosaic, and the one on the right is the normalized reflectance. So in order for a crater to be classified into the Copernican category, it needs to exhibit crisp morphology and bright visible rays. Craters that exhibit crisp morphology but no visible rays were placed into the Eratosthenian category, and craters that were older or degraded were placed in the older category. Ambiguous craters were those that exhibited crisp morphology, but faint rays were visible, so we weren't sure initially as to whether they were Copernican or Eratosthenian, but we later reclassified them into the Eratosthenian category using OMAT values. So these are all the craters that we've classified, around 11,800 of them, greater than 10 kilometers in diameter. So the red spots are the crater shapefiles overlain on top of the WAC monochrome mosaic and the normalized reflectance map. So this is the near side results. As expected, the number of Copernican craters are lower than the number of Eratosthenian craters. And again, for the far side, there are fewer Copernican craters on the far side as opposed to the near side, and I'll address that shortly. We then use the OMAT classification from Clementine to look at optical maturation. So fresh material has high albedo, whereas mature material has lower albedo. So we formed three categories based on the OMAT values. So category A and B were for Copernican, where craters that exhibited OMAT values greater than 0.22 or between 0.15 and 0.22. And category C with OMAT values less than 0.15. We said that they were part Eratosthenian and part degraded. So we found that not only are there more craters on the far side, but there are also a larger percentage of younger craters on the far side. The corresponding ratios between classes A, B, and C are similar, but not exactly the same for near side and far side. In the previous method, the selection of Copernican craters appears to be affected by compositional rays, and that's why we think that there are more Copernican craters on the near side than on the far side. And then we also we extended Greer's effort and so far found no evidence of increased number of impacts in the late Copernican era. And as expected, we found more craters, more smaller craters than larger. Progress so far, we've extended previous efforts by including crater size range down to 10 kilometers. We've also expanded the catalog of Copernican and Eratosthenian craters by nearly 8 times that of previous work. Furthermore, this catalog can be used to study crater degradation rates, regolith evolution, impact rates through time. In the coming months, we hope to complete the current classification work, compute cratering rates, check for near side, far side asymmetry, also classify smaller craters down to 5 kilometers in diameter using the same criteria, investigate crater degradation rates using OMAT and the WAC ultraviolet observations, and also compare with Mercurian craters. Thank you.
Increased the number of craters in a catalog by quite a bit. So is that, this is not working, is that available to the community? Where
it will be shortly when we finish completing the 5 kilometer range craters.
And where will we be able to find that? Will that be announced at
LPSC, or how's that going to work in terms of?
I think it will be announced at AGU or maybe LPSC.
Okay, great.
So with your catalogue, you've obviously looked at a lot of craters down to kind of a very small size. So have you found any particularly interesting or unusual craters that you've found in your study?
No.
Did you, in your study, did you try to distinguish between primary and secondary craters at all? And if you did, what were the characteristics that you used to distinguish between them?
Mostly secondary craters that occurred in clusters, we ignored them. But otherwise, this is only the first pass, so we're still working more to eliminate secondary craters in the future.
Any other questions? All right, thank you very much.
Thank you.